get the things that we're seeing in the environment today, we need a whole bunch of time. We need a whole bunch of time. And so what is time? What is time? Well, I don't want to get too philosophical here, and we're not going to become quantum physicists at the end of this slide, but what is time? Well, we don't need to know, again, the full-scale PhD level physics on what is time, but what I want you guys to understand for this class is the vastness of geologic time. What 4.6 billion years actually means. What does that mean? Well, I want you guys to picture, as you're sitting there, I want you guys to picture a stack of 100 single dollar bills. 100 single dollar bills. How tall is that stack? You might be able to picture that. I don't know. It's within maybe an inch or two, I would guess, somewhere in there. $100 bills would definitely be in that kind of range. Pretty small, right? Not towering, right? But in that range. What about $1,000 bills? How big is that? Well, about 10 times what I was picturing earlier, somewhere in there. What about 10,000 single dollar bills? What does that look like? Does that cover your desk? Is that enough to just cover a corner of your desk? What about 100,000 single dollar bills? How big is that? If you were to stack those all one on top of another, right, is that as tall as your ceiling, or is that your roof? What about 1 million of those? Well, now we really start to lose it. What about 10 million? What about 100 million? What about 1 billion? What about 4.6 single dollar bills? How big is that? I have no idea. I can't even picture it. The vastness, the size of that number is so big that I have a hard time contextualizing it. It's the same thing with time. If I ask you to think about a time a year ago and describe that as recent or ancient history, you would say, well, that was a little while ago. If I were to say 100 years ago, you would say, wow, that's way before my time. I don't know. Yeah, I don't know. But feasible. I can picture that. What about 1,000 years ago? What about 10,000 years ago? What about 100,000, 1 million years ago? We start to lose how much time that really means. And what we can essentially think of in terms of 4.6 billion years of time, we can think of that as an infinite number of possibilities for change to occur. 4.6 billion years of time represents so much opportunity for this planet to demonstrate how dynamic it can be. In that amount of time, we can raise mountains, we can erode them completely away, we can evolve new species we can cause, or we can see mass extinctions occur. So much change, it opens the door to all of it. That's what time does. That's what that amount of time does. So, in the vastness of time, how do we place ourselves? How do we place each chapter of the book back in sequence? Well, there's two main methods that we utilize for telling time. Those are absolute age dating and relative age dating, okay? Absolute age dating are techniques employed to assign a specific age to a group of rocks. That is, you take a rock and typically you analyze it chemically, and in analyzing that material chemically, it spits out a number. This rock is 500 million years old. Relative age dating is simply putting the rocks back in sequence. That is, this rock is older than that rock is older than that rock, and this is the youngest rock. That is relative age dating. And you might say to yourself, well, Saville, why don't we just do absolute age dating on everything? Because if I have absolute ages for everything, then I could rank them the same way that relative age dating allows us to do. And that's an awesome thought. The problem is that not all materials can be dated absolutely. If you were to go down to the beach and you were to analyze the sediments down at the beach, you would see that they came from the rocks in the mountains here above us in San Bernardino, in portions of Riverside County. That's where those sediments are coming from. Those sediments are derived largely from intrusive igneous rocks that were in place somewhere around maybe 100 million years ago or so. If you were to take those sediments and attempt to date the ages of those sediments, what age do you think those sediments would show up as? 100 million years old, right? Even though they're present at the beach today, and that's the environment that you're looking to age date, that number would be 100 million years old. So you can't absolutely age date all of these materials because not all of these materials represent a snapshot in time. And in some cases, the chemistry that's required to date these materials either isn't present or has been altered by processes involved in diagenesis. So relative age dating helps us to put the sequence back in order in those areas where we don't have our absolute age dates. So both of these are critical to our understanding of time in the rock record. So I want to take a look first at relative age dating principles. And to do so, I need to introduce you to Nick Steno. Nick Steno is really foundational in defining some really key principles of relative age dating. Nick Steno was interested in geology in a number of ways. One of the ways that he was interested in, he was identifying, or people were identifying these triangular shaped fossils that were serrated on the edges as fossilized dragon tongues. Nick Steno didn't buy it and changed the interpretation of these triangular fossils into being those of actually teeth of large sharks. And he was right. And in that work and that effort, he started to recognize that these teeth were coming from certain layers of rocks, and those layers of rocks seemed to be deposited in specific sequences, and that the sequences of that deposition of those sediments could absolutely be used to, again, put the chapters back in order, to not say exactly when these layers were deposited, but rather just to put them back in order. So what Steno came up with are what are called Steno's laws. Steno's laws, what are called now today Steno's laws. These are the rules that we use to determine the order in which rocks were deposited in. And we've got 4 of them: the principle of superposition, the principle of original horizontality, the principle of lateral continuity, and the principle of cross-cutting relationships. Okay. I would recommend maybe putting these things in your notebook with maybe a little bit of space between each one, because we're going to go through each one right now, define it for you, and talk about how it's going to be used. So a little bit of space in there might be good. All right. So starting with the principle of superposition. Principle of superposition quite simply states the stuff on the bottom is older than the stuff on top. If I showed you a stack of papers, maybe I was grading, and I had a stack of graded papers sitting there, and I asked you, which paper do you think I graded first? You would say the one on the bottom, right? Because I graded that paper and I put it down on the table, then I graded the next one and put that on top of it, and so on and so forth as I worked through the class, right? That's the principle of superposition, that stuff on the bottom is older, was deposited first before the stuff on top. So when you look at the Grand Canyon, those sediments that are lower down in the Grand Canyon are much older than those sediments that are present at the top of the canyon. That's the principle of superposition. The principle of original horizontality states that sediments are primarily deposited in a horizontal fashion. They are largely deposited in a fashion that's parallel to Earth's surface. There's a little bit of angle to most sediments as they're deposited, but in general, they're deposited in these horizontal layers. So where we see those horizontal layers are disturbed, right? Where we see they are disturbed, where they're not horizontal anymore, we know something's happened, right? We know that some geologic event has happened to tilt or deform those layers of rocks, all right? The principle of lateral continuity states that as we lay down, or as the Earth lays down layers of sediment, the deposition of that sediment will be laterally continuous until there is a change in environmental conditions. When you walk down the beach, say in Huntington Beach, the nature of the sand there stays the same until you get maybe down near Crystal Cove, right? Where the beach changes shape dramatically, things get a little bit more rocky. So if you think about that layer of sand that is currently sitting at Huntington Beach, if you were to bury it, that layer of sand would continue for that entire distance. If millions of years down the road, that sand turned to stone and then was lifted out of the ground and rivers cut through it, you might see that those layers are disconnected from each other, separated by that canyon. But the principle of lateral continuity says it's not likely that these layers were deposited separately. It's likely that this represented one continuous layer that since has been cut by the canyon. Okay. The principle of cross-cutting relationships states that those geological features that are cutting other geologic features are going to be younger than those features that are being cut. So here we see 4 layers of rocks labeled there, older to, or oldest to older, right? So the principle of superposition allows us to date this lowest most layer here as the oldest. Things are getting progressively younger as we move up, but then these layers are cut by this igneous dike. Because these layers are cut by this structure, the principle of cross-cutting relationships tells us that that feature doing the cutting must be younger than the remaining layers of rocks. It's not likely that that igneous dike was extending up into the air and then layers of sediments were deposited around it. Rather, that these layers of sediments already existed and then were cracked open and injected with molten material that then solidified as this igneous dike. That's the principle of cross-cutting relationships. So when we look at these principles, we can apply them collectively to take a block diagram like this one here and say something about the relative ages of all of these materials. That is, the principle of superposition allows us to look at these layers of rocks and say, okay, of these layers of rocks, this layer of rock at the bottom must be the oldest. But I noticed that these layers of rocks here, they are all caught, or they are all cut and moved and offset from each other by this fault right here, fault A. So it must be the case that these layers of rocks were deposited and then some earthquake happened and fault A was produced, and now these rocks have moved relative to each other. But then I noticed that fault A is cut by these overlying layers of rocks. So these overlying layers of rocks, they must have been deposited after this movement, so must be younger, right? All of these layers of rocks then are cut by dike A here, right? So dike A must be younger than everything we've mentioned so far. Dike A also cuts this sill, and dike B that cuts across all of these materials, right? So dike A must be younger than that feature as well. You can see that we can get really into reconstructing the geologic history of this area by applying each of these principles in reconstructing the relative ages of these materials, all right? When you look at inclusions of rocks that are included within maybe some intrusive igneous rock. Let's imagine that this rock here is maybe some sandstone, and the sandstone is undatable, but this intrusive igneous rock right here, it can be dated. And we date this intrusive igneous rock as 100 million years old, and we note that it includes some of those little clasts of that sandstone there. So in effect, this intrusive igneous rock here is cutting into this surrounding country rock, which means that it must be younger than those materials. So that tells us that these little inclusions here must be older than 100 million years old. So there we see a combination of both relative and absolute age dating. And there's a variety of circumstances where we can apply that, not just within the intrusion, but also in overriding layers of rocks. Again, if this is 100 million years old, if we see inclusions of that material in the overlying layers of sediment, we know that those must be younger than 100 million years old, right? Because now those materials are being included within that layer of rock. So again, combining these tools can be amazingly powerful, and what we're going to see is called bracketing of geologic ages. Okay? All right. So those 4 principles, plus one new and important concept. And again, as a geologist, I need to come clean and admit something on behalf of the profession, and that is, again, that the geologic record is imperfect. It's not perfect. There is not a continuous record of every event in Earth's history preserved in the rock record. As I talk to you guys, I pace back and forth on my floor here, and those shoe prints that I leave in the carpet, they will go away someday. The peaks of our mountains, they will go away someday. Actively, that's happening right now. And so again, as we mentioned when we talked about depositional environments, deposition, the recording of time, is not happening everywhere. In many, many places, erosion outpaces deposition. And in those cases, what we get is missing time, or what we call an unconformity. An unconformity, these are contacts between rock units where time is missing due to erosion. And there are 2 types of unconformity, what are called angular unconformities and disconformities. Angular unconformities are unconformities, like we're seeing here, where the rocks encounter each other at an angle, right? Thus the term angular unconformity. So in this situation, what we imagine is here's sea level, it's relatively high. And so we get a bunch of sediments being deposited, 1, 2, 3, 4, 5 here from oldest to youngest. Eventually sea level retreats, or some tectonic activity happens that results in these materials being uplifted and folded, right? Uplifted and folded, exposing them then to erosion. So erosion takes over and takes those rock layers. Maybe this uppermost rock layer here is 500 million years old. Erosion erodes those materials until about, maybe it's 10 million years ago, sea level rises again, and we get new sediments being deposited on top of these older sediments along this irregular angular unconformity, such that these sediments that might be 10 million years old are in direct contact with sediments that were deposited 500 million years ago. That's 490 million years of missing time. And that much missing time along these unconformities is not uncommon. And it's this sort of phenomenon that was being described by James Hutton in his discussion of the great unconformity that we talked about at Sakar Point. But we see these unconformities also present within our Grand Canyon. You look at the Grand Canyon and you see these amazing layers of rock, and you think, wow, those were just deposited one after another from what seems like forever ago. And in some cases that's true, but not in all. And in fact, there are portions of the Grand Canyon where you may have as many as 1 billion years of missing time along these so-called angular unconformities. In fact, at the base of the Grand Canyon is another angular unconformity commonly referred to as the Great Unconformity because of how much time is missing there. But another type of maybe more sneaky unconformity exists, or bit of missing time exists, and those are called disconformities. Disconformities. So angular unconformities oftentimes involve some sort of tectonic activity. Disconformities can actually involve just changes in sea level. So sea level is high, you're getting sediments being deposited. Sea level falls, and you start to get some erosion. So no deposition during those times. And then sea level rises again, now renewed sediment deposition. We start to record time again, and back and forth, so on and so forth. And these disconformities can be really sneaky and subtle, but they can represent really significant amounts of missing geologic time. Here's a disconformity here between this sandstone above, limestone below, that represents more than 40 years of missing, or 40 million years, excuse me, of missing time. So recognizing these things in the rock record is a challenge, and it oftentimes requires some really detailed geologic mapping to map these surfaces where signs of erosion are obvious. But really, again, some detailed field effort to do so, and can have some significant impacts on how we interpret the rock record. All right. So again, we can utilize these principles to reorganize rock units that have been faulted or tipped and weathered, etc. So if you were given a block diagram like this one here, we could apply the principles of superposition and cross-cutting relationships and lateral continuity, horizontality to tell the story of these rock units. And the way we would do that, again, we would start with our oldest rock unit. So we would say, okay, superposition, it's got to be this one. We're going to assume that all of these were deposited in sequence. So A, B, C, and E, right? Because D is actually a sill. So A, B, C, and E were deposited. And then eventually sea level, it retreated. Maybe there was a little bit of uplift, right? To where some igneous activity also happened, and we get D coming in here, right, and squeezing its way between C and E. So we get this sill, we get some continued igneous activity with the emplacement of this dike here, F. This dike cutting across D and E and A, B, C, D, and E tells us it's younger than all of those rock units, right? Then those layers are all tilted, right? So there had to have been some tectonic activity to tilt them. That's what the principle of original horizontality tells us, right? And then there was continued erosion that eroded this flat top along that angular surface now, right? Along that angular surface. Then eventually we get sea level rises, more sediments are deposited, and now we've got this angular unconformity between this set. Again, by utilizing these principles, we can tell a really detailed story regarding the history, the geologic history of an area. All right. So with that said, exercise time. Let's go ahead and do this on our own. That is, if I were to give you a block diagram like this, could you put the sequence of these units back in order and say something about the geologic history of this area? So that's what we're going to do together right now. So let's go ahead and do that. All right, our first task will always be, so geologists, we always like to work from old to young, right? Old to young. So always first step, go ahead and find that oldest unit. And a great place to start in looking for the oldest unit is to start right near the bottom of the block because of our principle of superposition. So we see down here near the bottom, I, J, K, F, G, H, B, D, E, and we ask ourselves, well, which one's older? Well, down here at the very bottom, we have J, but we also have I, and we have G. Well, J is cut by G, so it's got to be older than G. And J is also cut by I, so J has got to be older than I. So let's go ahead and start then with J being our oldest rock unit, okay? And then we're going to assume that these layers here were deposited in sequence. So we've got J, K, F, and H. J, K, F, and H, all right? Principle of superposition at work there. But now what? Which one's the next oldest? Well, we have G, I, B. We have this fault here, D, right? That's what's being pointed to, is this little fault here, just as a for fun exercise for earthquakes and faults. If you guys remember, maybe an exam or quiz style question for the future. What kind of fault is D here? You would say, well, Sapfield, I remember that's a dip slip fault. And I would say, fantastic, what kind? And you would say, well, that's a normal dip slip fault because the hanging wall block has moved down relative to the footwall block. All right, just a little refresher. Why not, right? Why not? Awesome. All right, so J, K, F, and H. We have these all remaining. Well, is it G? Well, G looks like it's cutting B, so it's got to be younger than B, right? So is it B? Well, B is older than E because of the principle of superposition, and B is also cut by D. So it must be older than D, right? It's also cut by I. So yes, so B must be our next youngest unit. All right, so there's B. Now what? Well, let's first take a look here. What kind of contact is this between J, K, F, and H, and B? What do you guys think? What do you guys think? Well, if you said that that is an, I'm going to just label this as an AU, angular unconformity, you were exactly right. That's right. That's an angular unconformity right there. That represents these layers were deposited horizontally and then uplifted and eroded, and then B was deposited on top of them. Great job. Great job. So now what? So B, is the next one G, D, E, I, C, or A? Well, let's see. E is above B, but look at E also cuts this G here, right? So G, right, being cut by E, G has to be older than E, right? E is cut by D, so E must be older than D, right? So, and then D is cut by I, so D must be younger than, or excuse me, older than I, right? That leaves us really only one option. Our next youngest unit has to be G, right? Has to be G. All right. Okay, so now G, right? We've got E, I, D, C, and A left. Well, we know C and A, principle of superposition is not going to be those, right? So we really have E, I, or D next, right? So we got to determine which is the oldest of those three. Is it I? Well, I cuts D, so I must be younger than D, right? So that doesn't work. So it's either E or D. So E is cut by D, so D must be younger than E. So our next unit must be E. We also notice that E here is cutting G across this horizontal plane that's parallel to B. Does anybody remember what that feature must be called between E and G and B here? If there's some erosion along the surface here, that's called, starts with a D, rhymes with Bliss conformity. That's right, it's a disconformity. So I'm going to label that just as a conformity. That's right, it's a disconformity. It's a disconformity right here. Right here between E and G. So I'm going to label that just as a disc. All right, so that's a disconformity there, right? So again, sea level must have fallen or something happened to where then erosion took over, and now you have this bit of missing time between these rock layers. All right, so now we've got I, D, C, and A. Again, C and A, we don't have to worry about those yet. Let's take a look at I. Is I or D older? Well, I is cutting D and isn't moved by D, so I must be younger than D, right? So our next oldest unit is going to be D, right? It's going to be D. So now is I older or younger than C or A? Well, we can see that C is cutting I, and C also contains some inclusions of I here, right? So C must be younger than I, right? So I is our next oldest unit there, right? And then again, what do we have between now C and E? Well, look at, we've got C has cut this fault here, right? It's cut D, right? It's cut I, right? Along this, what would be an erosional surface, right? And so this must be, right there, another of our disconformities, right? Another of our disconformities. All right. So then after I, right, we've just got to use the principle of superposition, and pretty straightforward. We've got C and A, and that's our sequence. And not only did we get the sequence of these rock units, but we told the geologic story of this area. We've got deposition of J, K, F, and H. Those materials were then uplifted, eroded, and then we produced this, thus producing this angular unconformity. Then we get the deposition of B. B was then intruded by the igneous dike at G. G was then eroded along with the portion of the top of B. Subsequently, then E was deposited on top of it. Then there was an earthquake. There was some faulting that produced fault D. After that, those materials were buried. There was some intrusive materials then came in and entered into those lower units. That material was then eroded again along another disconformity. Then eventually sea level rose and C and A were deposited. That's the power of relative age dating and applying these principles. And so what you guys want to be prepared for is make sure that you know how to do this exercise, because you may see a similar block diagram on a future quiz or an exam. So make sure that you can do this exercise. And as always, if you have any questions at all, please don't hesitate to let me know. All right. It's kind of fun. It's like a puzzle. It's kind of neat. All right, cool. Let's keep on going. All right. Well, that's really fun. But wouldn't it be great what if we had layers of rocks in China, and we wanted to be able to say something about the age or the timing of those layers of rocks in China as related to layers of rocks that we find in Death Valley? How do we say that those layers are maybe of similar age or different age? That is, how do we correlate them? Especially since we see that there are sandstones that may be 1 billion years old, and there may be sandstones that are 1 million years old. We can't just use the type of rock that it is. So how do we oftentimes correlate between rock units? Well, prepare yourselves for one of my favorite aspects of geology, and that is, those are indeed fossils. Fossils are oftentimes how we do it. Life is amazingly diverse on this planet. It's really diverse, and it's really, really diverse through time. Evolution provides us with snapshots in time. Species, they come and they go all of the time, whether those are very small organisms, little microorganisms living in the ocean, or that's really large vertebrate animals living here on land. Those animals sometimes have, not just animals, plants too, those fossils, that evidence of life provides us with an important resource, not just for saying how big a dinosaur was, but also for telling time in the rock record because of evolution as a constant element of life. But again, I need to confess, on behalf of geologists everywhere, the fossil record, it's not complete. It's not perfect. It's not perfect. In fact, you can witness the imperfection of the fossil record today, right? If you drive, if you took a drive, you may have an insect that gets stuck to your windshield. And that sad event, that capturing of that insect on your windshield there, almost certainly completely rules out the potential of that insect ever making it into the fossil record. It is gone. The chances of it making it in the fossil record, not going to happen. In fact, the chances of most life on this planet of making it into the fossil record is extremely limited. It is not likely at all that any specific animal is going to make it into the rock record. Though there are some elements of both the biology and the environment that can make conditions more favorable for preservation. One of those is rapid burial. Rapid burial. Organisms that live in environments where deposition can happen very rapidly. That rapid deposition removes the potential or limits the potential for the carcass of that animal or that plant, or whatever the case may be, from being consumed by other animals, or being consumed in some cases by bacteria. So rapid burial removes a lot of the environmental pressures on preservation of those organisms. Another favorable condition is the preservation or the presence of hard parts. Hard parts, our bones, right? Our bones are much more likely to be preserved than our skin. And that's because that material is composed of mineral. It's apatite, our skeletons, but the shells of marine organisms, oftentimes calcium carbonate. These hard tissues make them very resilient. The hardness of these tissues, the resilience of these tissues makes them very resilient, makes them very resistant to biodegradation, to mechanical breakdown. And so they can stick around for a long time. And the longer something can stick around, the more likelihood that item has, or that animal or that plant has, to make it into the fossil record. So what we see is a fossil record that's biased towards those things. Those animals that lived in those environments, or at least had their carcasses transported to those environments, those animals that contain those hard tissues, those organisms that contain those aspects that are resistant to being removed, those are the concentrated elements in the rock record. When we look at the number of species that exist on this planet today, the number of species that we currently have described in the fossil record pales in comparison because, at least in part, because of these biases. But that doesn't mean that the fossil record isn't useful, nor does it mean that the fossil record isn't abundant, nor does it mean that the fossil record isn't diverse. The fossil record is amazing. In and around Riverside County, we can visit multiple localities, and we do with our field classes. We visit multiple localities and pull fossils out of the ground all of the time. The fossil record is actually really abundant. And the fossils that we see there, like these ammonites here, can preserve a high level of detail. Ammonites were a really diverse group of organisms. They went extinct with dinosaurs. Sadly, the overshadowed by the extinction of the dinosaurs. But this really diverse group of organisms, these things had some really ornate shells. They were very a rich part of our oceans. These shells, you would have seen the organism, the soft tissue of the organism resembled a squid that would have come out of the open end of these shells. Inside of these shells was a tube called a siphuncle that the animal would use to fill different chambers in the shell with gases so that it could go up and down in the water, all kinds of really, really neat stuff. But they swam the world's ocean. And so we can find them in sediments all over the place. Here in California, we have huge deposits of ammonite shell debris, particularly in Northern California. Similarly, trace fossils we can use to tell time too, because in the same way that the form and function of animals has changed through time, their behavior has as well. Just like we've seen animals gain complexity in their overall being, we see complexity in their behavior as well. We see that early animals largely meandered just kind of what looks like somewhat mindlessly along the seafloor, whereas subsequent animals became increasingly complex in the way that they mined sediments, in the way that they moved, the way that they traveled. Dinosaurs and the anatomical requirements to be able to run in that way is an absolutely awesome aspect of the history of life. And we see that not just in dinosaur footprints, but also in the burrows of what were likely invertebrates. So trace fossils, oftentimes we can't associate with a specific animal group, right? So trace fossils, ichnofossils, we talked about these when we discussed depositional environments. These trace fossils, this evidence of animal behavior, most commonly can't be linked to a specific type of crab or shrimp. But the behavior can represent unique windows of time, unique environments too. And this fossil here on the right is one of my favorites. This is a trace fossil called Ophiomorpha. Ophiomorpha was a burrow that likely was maintained open, maybe by some kind of crustacean. They're a modern shrimp that make very similar burrows. And the way they do it is as they dig down, they take little bits of sand and they make little sand balls. And then they take their mucus and they spit into the sand ball and they pack it down. And then they take that sand ball and they put it up against the side of the burrow, kind of like a brick. And brick by brick, they build this Ophiomorpha. And if you look at these spiral staircase forms, you'll see those small pellets stuck on the side there. You can find these as close to San Diego. Beaches down in San Diego, you can find some really neat Ophiomorpha fossils. Really complex behavior, right? Really complex behavior. And those behaviors are also constrained in time. Animals that were 575 million years old did not make these types of structures. And so with the advent of these new behaviors become increasingly complex. Trace fossils. Another interesting type of trace fossil is something called a coprolite. Coprolite. What do you think that is? Yeah, that's fossilized dung, no doubt. That's exactly what that is. In fact, we used to, I used to be able to participate in grad school. We had developed this outreach program where we'd get to go in and teach elementary school classrooms about fossils and volcanoes and earthquakes too, and all kinds of cool stuff. But in our fossil collection, we had a coprolite. It was really funny. You take the coprolite, which is just stone. Bacteria, as they degrade the fossilized poop, there's some specific special circumstances where they completely replicate the structure of what it is they're degrading, albeit in stone. So there's no fecal particles in this at all. You take the fossilized poop and you give it to the classroom there, and they pass it around. And you tell them to try to guess what it is. And every now and again, one of them would guess, and you'd see them as they were passing it around. The word of what it was would get out, and they would get so excited and grossed out, and they'd bring it up to the front of the class and say, "So what do you think this is?" And they'd all exclaim, "It's fossil poop!" And you'd say, "That's exactly right." And fossilized dung like this is actually really insightful because, again, it gives us a picture of the internal anatomy of the organism, which oftentimes is not preserved, but we can also see the things in which the animal was eating. You can still, even though this is all turned to stone, sometimes see some of the materials still preserved in these coprolites. And again, by doing so, you can see where certain organisms may have coexisted and then use information that you might have for some of those other types of fossils to, again, constrain geologic time. So fossils obviously key. And there's a specific type of fossil that's really key for telling time. And those are what we call index fossils. Index fossils. Index fossils are fossils of organisms that existed over a narrow age range. So a narrow window of time, species that existed over a very narrow window of time, but over that narrow window of time achieved a very wide geographic distribution. That is that you might find that specific type of ammonite in a layer of rock both in China and in Death Valley. You might find that fossil in both those places, right? And so you can use that to say that the ages of these materials is likely the same. That's what we would call an index fossil. And so we utilize, usually it's not just we're looking for one specific fossil. We might look at a collection of fossils and their age ranges and distribution to help constrain relative ages of materials, ultimately absolute ages in some cases. So here we have two rock layers, both of which contain fossils. Rock unit B there contains some fossils. There's a trilobite here is what this little critter is right here, one of my favorite fossils. We've got, this is a brachiopod, looks like maybe a scallop there, plant fossil, all kinds of cool stuff. And we look at the age ranges over which the times that we know that those fossils may have existed. And so in doing that, we look at the age at which all of those fossils age ranges, they overlap, right? So it's not any one fossil, it's the collection of fossils that we utilize, and where those time frames overlap, that helps us to narrow down the potential age of that layer of rock. Same thing for rock unit A, where we see a different collection of fossils. We know it must be younger, and when we do this overlapping age dating technique, it helps us to narrow down the age of those materials. So obviously fossils really important. What can they tell us? Well, they can tell us the age of the rock, but obviously from just a life standpoint, they can tell us stuff about ecology, biology, evolution. Right? So digging into the fossil record is super important. Also can tell us something about environmental changes. Again, one of the most sensitive indicators of environmental change is changes in the biosphere. Changes in community structuring, extinction or appearance of animals speaks so loudly and so sensitively to environmental change. And so looking at the fossil record can sometimes give us indication as to a change having occurred. It's part of why we look in modern environments and we see coral reefs decline, and that causes so much pause among scientists, is because what we see in the geologic record is that in significant events in the history of life, where we've seen life take a hit, one of the first groups that we consistently see take that hit, you guessed it, they're coral reef ecosystems. They're very sensitive to global environmental change. So again, the type of environment, fossils very insightful for environmental reconstructions, because again, really sensitive to what's going on in the world around them. All right. Well, let's then dive into our discussion on absolute dating. All right, Sevenfield, I get the sequence thing. I get how we use fossils, but I want some numbers now. I know you've told me the Earth is 4.6 billion years old. I know we've talked about animals that are more than 500 million years old. All we've discussed now is a sequence. How do you know those numbers? Well, it's via these methods called absolute dating. Absolute dating methods are where we're now going to look to get a number. How old is this fossil? How old is this rock? How do we do that? Well, primarily, we do these absolute age dating principles in igneous rocks. In igneous rocks is primarily how we do that. And that's because igneous rocks, and that again includes not just intrusive igneous rocks, but also things like volcanic ash layers, sills and dikes. Those, the formation, the collection of those materials captures a moment in time. It captures a snapshot, moment in time, which is what we need, because again, with our beach example, if you test those sediments that are 100 million years old being deposited at the beach today, and we want to know how old the beach is, those sediments are only going to tell you they're 100 million years old, right? So again, igneous rocks are going to be really helpful. And where we can find things like layers of ash embedded within and among sedimentary rock layers, those are going to be really insightful for telling time. Much of this practice of absolute age dating relies on the specific use of specific types of elements. We looked at the periodic table earlier on this semester, and I noted that there are elements on that periodic table that are defined as separate elements from one another based on the number of protons present within the nucleus of each of those atoms. The number of protons defines what element it is. Hydrogen has 1 proton in the nucleus. Helium has 2, so on and so forth. But what I didn't mention is that there are various versions of many of these elements. And so there are different versions of hydrogen. And what defines them as different is the number of neutrons in the nucleus. So hydrogen will always have one proton, but there are certain types of hydrogen that have no neutrons in the nucleus. There are certain types of hydrogen that has one neutron in the nucleus. We call that deuterium. There are some types of hydrogen that have two neutrons in the nucleus, and that's what we call tritium. Tritium. Each of these types of hydrogen, we refer to it as an isotope of hydrogen. And many elements have different isotopes. Carbon has several isotopes. Oxygen has several isotopes. And what's really unique is that some of these isotopes are not happy being what they are. They're not happy being what they are. That is, they are radioactive. They are radioactive. They're unstable. They're really not happy being what they are. And so hydrogen, again, a great example, hydrogen and deuterium, again, deuterium, just hydrogen with an additional neutron in the nucleus. They're both perfectly happy being what they are. No change, right? Tritium, not so much. Tritium is radioactive. It's unstable. It will go through a process called radioactive decay. And what's really important to note for this absolute age dating discussion is that radioactive decay, the rate of that decay is constant. It's constant for this element. It's constant and specific for this element. It's driven by physics and thus can be utilized as a timekeeper within our rock units. All right. So again, just to remind you the structure of an atom, what we're talking about right now is the nucleus of the atom. We're talking about the number of protons. Again, that's a constant for each atom, but it's the number of neutrons that varies among what we call an isotope, and certain isotopes radioactive. So all isotopes, radioactive isotopes, what they start out as is what we call a parent isotope, or the parent material, right? The parent, that is the unstable isotope. And oftentimes that parent material is identified by its elemental symbol or name and a number, right? So carbon has 6 protons in the nucleus, always. The most common form of carbon also has 6 neutrons in the nucleus. However, sometimes there is carbon that has 7 neutrons in the nucleus. Both of those forms of carbon, those with 6 neutrons in the nucleus and those with 7, those are both stable forms of carbon. Carbon with 6 neutrons in the nucleus, we call that carbon 12, because 6 protons plus 6 neutrons, that's carbon 12. Carbon with 6 protons and 7 neutrons in the nucleus, we call that carbon 13. And both carbon 12 and carbon 13 are stable forms of carbon. Sometimes you get carbon that has 8 neutrons in the nucleus. 6 protons plus 8 neutrons, that's carbon 14. And you may have heard of carbon 14, and that's because carbon 14 is commonly utilized in dating of things like archaeological artifacts and some really interesting stuff. And so you've maybe heard of carbon 14 for those reasons, and that's what that 14 is referring to, is again, the number of protons plus the number of neutrons in the nucleus. So again, carbon 14 is unstable. It's the parent material. It goes through a process of decay where it decays into a new element, a new material. That's what we call the daughter material. And that daughter material, in some cases, for some elements, may also be radioactive and thus may go through further processes of decay. But this parent to daughter, right, is the key step right there. And again, the rate of that decay is constant and is described in terms of what's called a half-life. Half-life, it's constant, but it's also proportional to the amount of parent material that is present. That is, if you have 100 units of some radioactive parent isotope, right, as it decays, right, there's less and less parent isotope available to further decay. So the amount of parent that's changing to daughter, right, that decreases through time. So the best way to describe the rate of that change is what's called the half-life. And again, that's the time needed for half of the parent to decay to daughter. So if you were looking at a material and it contained 50% parent isotopes and 50% daughter, then that means that one half-life has passed. If you've got 25% parent and 75% daughter, that means now you've had 2 half-lives pass, and so on and so forth. So eventually what will happen is your parent material will run out. You'll eventually get to 0 parent material left. And at that point, your clock stops working. And typically that occurs after about 10 half-lives, right? About 10 half-lives. I'll tell you that carbon-14 has a half-life of more than 5,000 years. But let's assume it's 5,000 years for right now. 10 times, let's assume it's 6,000 years, actually closer to 6,000 years. 10 times that 6,000 year half-life, we're being generous there, is 60,000 years. That means that carbon-14 has a rough time. You have a hard time dating things that are older than 60,000 years or so. Applying carbon-14 dating to something that is 2 million years old, you can't do it because that material will have long gone what's called carbon dead. That is, all that parent material has decayed. So how do I know that there are rocks that are 500 million years old? Well, that's because there are many more radioactive isotopes than carbon-14. In fact, there are many radioactive isotopes out there. Unfortunately, many of them have varying half-lives, or they all have different half-lives. Rubidium, strontium, 47 billion year half-life. We might be able to utilize that resource then for doing things like dating the age of the Earth, right? Uranium, lead, 4.5 billion year half-life. Uranium 235, lead 207, 713 million years, right? Potassium, argon, 1.33 billion years. Argon is another one. There are all sorts of parent-to-daughter decay relationships with known half-lives such that we can utilize those chemicals when available, to tell ages in rocks, right? Tell ages in rocks. So again, the principle here is that we start out with a known quantity of both parent and daughter isotopes. So in this first beaker here, we see that we've got 20 parents and 2 daughters, right? We know the starting point. One half-life passes, so 10 of those parents are then converted to daughters. So we take that 20, we cut it in half, that becomes 10 parents, and then we add those converted parents to the daughters. So now the daughters, we add 10 to there. Another half-life passes, the number of parents cuts by half, right? And those 5 parents then are converted into daughters. And so if we know how many parents and daughters we're starting with, and we know the half-life of these materials, then we can utilize a curve like this one to say the exact age of a rock. That is, if I were to tell you that we've got a material that contains 13% parent material to 87% daughter product, and I were to ask you how many half-lives have passed through that window of time, you would say, well, there's 13%. So 1 half-life would be 50%, 2 half-lives, 25%, 3 half-lives, 12.5%. Let's go ahead and round up 13%, right? So you would say there's 3 half-lives past saphened field. And if I told you each half-life is worth, or each half-life for that parent isotope is 5,000 years, you would say, well, then the age of that material is simply the number of half-lives times the half-life, the actual time required for that decay. So 3 times 5,000, that material is 15,000 years. That's absolute radiometric or radioactive age dating in a nutshell. Let's take a look at how this applies to carbon-14. Let's take a look at carbon-14 and how it works. Carbon-14, there is a lot of nitrogen in the atmosphere. A whole lot of nitrogen in the atmosphere there. All right. And so that nitrogen is sitting there with its 7 protons floating about in the atmosphere, and also with its 7 neutrons. Up also with that nitrogen, the majority of the air you breathe is actually nitrogen. A little more than 70% of the air you breathe is nitrogen. And so all that nitrogen, there's a bunch of neutrons kind of floating around up there too. Those neutrons get a little excited when the sun shines on them. Those cosmic rays, they excite that neutron, and those neutrons start going a little crazy, and they bounce around and they go slamming into that nitrogen floating around in the atmosphere. And in doing so, they abruptly eject one of the protons from the nucleus of that nitrogen. So when that happens, the nucleus gets the addition of a neutron. So now there are 8 neutrons in the nucleus. And importantly, there's 1 less proton. There's only 6 protons in the nucleus. So that is no longer nitrogen. It is now carbon, and that is carbon-14. So there is a relatively constant amount of carbon-14 in the atmosphere in this process. A lot of that carbon-14 is going to be incorporated into things like carbon dioxide. That carbon-14 is absorbed by the plants through photosynthesis. And so the amount of carbon-14 that's within the plants remains in relative equilibrium with the atmosphere as long as that plant is alive. the animals that then are feeding on that plant material and the animals then that are feeding on those animals, they also are in equilibrium with the amount of carbon-14 that's present in the atmosphere. And so as long as plants are photosynthesizing and we're consuming that freshly dead plant matter and other animals that are doing the same, the carbon-14 balance among living things remains, again, relatively imbalanced with the carbon-14 in the atmosphere. That is until those materials die. When those materials die, they stop taking in new carbon-14, and that's when the clock starts. Once these animals and these plants stop taking in new carbon-14, the process of decay begins, and it's not that decaying carbon-14 is not replenished by new carbon-14. So following death and burial, right, this dead material here goes through, again, that process of decay, and that process of decay is relatively constant. Carbon-14 decays at a half-life of around 5,740 years or so. So after around 6,000 years or so, half of that original carbon-14 is going to be converted into daughter elements. So let's do an exercise here now utilizing carbon-14. Carbon-14 has a half-life of 5,740 years. Charcoal, or we find a charcoal specimen that has 12.5% carbon-14 versus what is found today in currently living tissue. Now, these two questions: what is the age of the charcoal, and what does this mean for the age of the rock unit containing it? Well, let's look at the age of the charcoal. We have what we need here, right? We have all we need to determine age, right, is we need the number of half-lives times the half-life, right? The half-life rate, we'll call it. Okay, so the number of half-lives times the half-life rate, and that will give us equals the age of the material. Okay, all right. So we have given to us the half-life rate, right? So we don't know the number of half-lives yet. That's our, we'll call that A, right? Our unknown. But we do have the half-life rate. That's 5,740 years, right? So let's go ahead and solve for A. So A, the number of half-lives, that's just going to be given to us by the percentage of parent material remaining, right? So if there's 12.5% of that carbon-14, that is our parent material there, we know that we started out with 100%. After one half-life, we have 50%. After two half-lives, we have 25%. After three half-lives, bingo, we've got 12.5%. So our A, our number of half-lives equals 1, 2, 3. So to determine the age of the materials, then we just need to go 3 times 5,740, right, equals, my calculator out here, 3 times 5,740 equals 17,220. That's our age. So the age of the charcoal is 17,220. So if there's a rock that's containing this charcoal, that is, this charcoal is included within a layer of rock, our principle of cross-cutting relationships tells us, well, that inclusion has to be older than the layer of rock that contains it, right? So that layer of rock has to be at least, right, or excuse me, at most this old, right? It has to be younger than that 17,220 years, right? Because again, this stuff had to have been made for it to be included within that rock layer. All right. So an exercise like that one, most certainly one that you want to be able to do. Again, calculate the number of half-lives, multiply that times the half-life rate, and that's going to give you the age of those materials. All right. All right. Let's see how this applies then in real life, right? Let's see how this applies in the geologic record. That is, let's imagine that we've got layers of rock here. We find a lot of these layers of rocks down here in the American Southwest. We've got the Dakota Sandstone, the Mako Shale, and the Mesa Verde Formation. We're wondering how old those are. Well, we know the Dakota Sandstone is older than the Mako Shale, which is older than the Mesa Verde Formation, right? We got those relative ages, but relatively, how old are those? Well, that's where we need some absolute age dating to bracket the ages of those things. And so we find this volcanic ash bed and we utilize some fancy machines to see how old that stuff is. And we see, okay, that ash bed is about 160 million years old. Our next igneous material, our next datable material is up here. It's this dike, and we date that material, and it is about 66 million years old. So what we can say, all we can say, is that the Dakota Sandstone, the Mako Shale, and the Mesa Verde Formation are all collectively between 160 million years old and 66 million years old. We can't just divide these up and say, well, this one then must be 150 and this one 100 and this one 70. You can't do that because you don't know how fast these all might have been deposited at within the same year for all you know. So all you can really do is bracket these things. And again, that's why applying both our radio active dating techniques, you've also heard me use that term. You'll hear it sometimes out in the wild referred to as radiometric age dating or absolute age dating, right? We can't do it in all materials, right? And so oftentimes we're left to simply bracket these things best we can. And that can be relatively imprecise at times. And oftentimes the pursuit for research scientists is going out and trying to improve on these ages. That most certainly can be a fruitful effort. So obviously, again, radioactive dating, it's not a perfect relationship, right? It's not. It's not that we can just go out and find every layer of rock and throw a number on it and be done with it. You can't do that, right? Because one, you need some datable materials, right? You need materials that contain those chemicals that can actually be used as that timepiece. There's also many sources of error that have to be detected and corrected for, oftentimes associated with diagenesis. That is, you need a closed system. You can't start with daughter atoms, right? You can't have daughter atoms in there to start with. Otherwise, that's going to throw off your percentages of parent versus daughter. You also can't release parents into the wild. Sometimes heating up rocks can actually change their chemistry, right? And when you do that, you force some of those chemical ingredients out into the atmosphere or into, the surrounding environment. So you got to have a closed system, and that's not always cheap. You also got to go out and use some really good field collection methods. You've got to collect good rock. That oftentimes will require drilling. That'll require some complex and expensive machinery. There's also the problem associated with using the wrong isotopes. If you had a rock that was 5 million years old and you dated it with carbon-14 and you said, well, there's 0% parent atom in there, so this rock must be 60,000 years old, you would obviously be wrong, right? Because you've utilized the wrong isotope. And so there simply might not be the right isotopes available within any given rock sample. So opportunities for radioactive dating, they are not ubiquitous. They're not everywhere. You've got to go out and you've got to find those special opportunities to do so. And when you do, they can be insightful. And so ultimately, what we have to rely on are both absolute and relative age dating techniques. And interestingly, these techniques come together to formulate what's called the geologic timescale. Geologic timescale is a way for geologists to, one, divide time, take the 4.6 billion years of Earth's history and group blocks of time within that at varying scales, such that when we talk about the period from 250 million years ago to 66 million years ago, we can do so concisely by simply saying the Mesozoic. Right? So it facilitates really quick and efficient discussion, but it also separates out significant moments in Earth's history and identifies those as being significant events. And so the geologic time scale is separated out, just as we saw with our depositional environments discussion with formations and members and those sorts of things. Geologic time is similarly separated out into these varying sized bins. The geologic time scale separates time into eons. Eons are separated into eras. Eras are separated into periods. Periods then are separated into epochs. Epochs can be further subdivided into stages. And here's what a portion of that looks like. This is the last 540 million years or so of the geologic time scale. That last 540 million years is defines an eon on the geologic time scale called the Phanerozoic. The Phanerozoic eon is separated into 3 eras: the Paleozoic, the Mesozoic, and the Cenozoic. And you can see that those eras are not equal in time. It's not simply dividing this into equal thirds. And that's because in the Phanerozoic eon, significant events in life's history is what divides up the eras within the Phanerozoic eon. The largest mass extinction in the history of this planet that we've currently discovered happened at the end of the Paleozoic, approximately 250 million years ago. Wiped out more than 90% of the stuff living in the ocean. Much bigger event than the extinction of the dinosaurs. The extinction of dinosaurs, big event, and actually marks the end of the Mesozoic era. The Cenozoic era is the era that we live in here today. So within each of these eras, there were significant events in the history of life too, and that results in further subdivision then of the geologic timescale into what are then called periods. So the Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian, Triassic, Jurassic, Cretaceous, Paleogene, Neogene, Quaternary are each periods on the geologic timescale where the stop and the start of each of these periods represents a significant event in the history of life. The base of the Cambrian period is actually noted by the appearance of animals which could actually dig down into the sediment rather than simply crawl along it, which has a bunch of implications for the anatomy of animals changing through time. The subsequent periods are marked by extinction events, appearance and extinction events that happen at the end, at beginning and ends of each of these periods. So again, it's a matter of bending time, being facilitating efficient discussion, but also recognizing these significant moments in Earth's history. And the geologic timescale is constantly being updated and revised. And in fact, you can see that in looking at the extinction of the dinosaurs event. You may have heard the extinction of the dinosaurs event referred to as the KT mass extinction. And that referred to what was the Cretaceous Tertiary boundary, which was right here. You can see now that KT boundary is no longer a KT, right? It's now it's K is a common symbol used for Cretaceous and geologic mapping and things. But now it is KP. The Tertiary no longer exists. It's been replaced by the Paleogene. And so now you'll hear it referred to as the KP mass extinction. You might also notice this Quaternary right here. Up until a few years ago, the beginning of the Quaternary was around 1.8 million years ago. That was recently revised to 2.6 million years ago based on some new discoveries. So this is in a constant state of flux. And so I bring that up for not just geologic timescale learning stuff, but life learning stuff. And that I've seen people in the past very into geology, and that's wonderful. Get the geologic timescale tattooed on their person. I'm going to advise against that because you might find your permanent tattoo out of date unless you're really dedicated to one specific geologic timescale. I would maybe recommend rethinking that decision, as this thing is constantly changing. So please be familiar with this geologic timescale. What you might see on a future quiz or an exam are portions of this geologic timescale blocked out, in which you're asked to, maybe I block out the Permian here and I replace it with a big letter C, and I say, which of these blocked out areas belongs to the Permian? And you would say, that is C, something along those lines. Or maybe I ask you, what period on the geologic timescale comes after the Permian? You would say the Triassic. Or what era follows the Paleozoic? You would say the Mesozoic. Okay, so that's some big takeaways. You definitely want to know this geologic timescale, certainly an important part of the study of geology. All right, so in summary, geologic time, it's vast. It's really vast. And the ages of different materials are determined relatively and absolutely. That is, relative to each other and with numerical ages defined and provided. And it's the combination of these things and the complex methods that go into all of these things, the detailed fieldwork that goes into these things that defines our geologic timescale and our discussions of geologic time in general. All right. So with that, that concludes this module. I'm going to once again wish you all an absolutely wonderful time. I hope everything is going great. As always, please feel free to get a hold of me anytime. I'd be more than happy to answer